introduction. And thanks for coming. My name is Wang, and I'm from Tsinghua University of China. It's my pleasure to present our works about sharing subtype of polymorphic objects. Modern software systems tend to integrate different software modules to accomplish complex functionality. Therefore, communication between among these software modules becomes inevitable and crucial. We all know that the shared memory is the fastest form of inter-process communication, or IPC. But commercial IPC frameworks are always built based on socket. Why is that? In our opinion, one of the reasons is that shared memories always introduce other issues. One of them is pointers. A pointer is actually the address of a memory location, which is meaningless to another address space. So we have to seek some solutions. Common solutions include serializations, such as we have proto-buffers of Google, Pickle for Python, and JSON for JavaScript, and so on. But the serialization process is introduced overhead, especially if the message is large. Another solution is to replace pointers with relative offset, such as the Boost library provide us a class named offset PTR. Well, it takes the developers some labors, but at least developers can still handle these explicit pointers. But how about the implicit pointers? For example, the virtual table pointers, or VPTR. These pointers will point to the virtual table. Well, in the object points to the virtual table. And they are generated by compilers to support subtype polymorphism. But there's no guarantee that the virtual tables of the same class are at the same location across different processes. So if we directly share the object, the VPTR means nothing to the other process. 2 years ago, researchers from UIUC present two solutions. The first one is named the DVT technology. When they share polymorphic object, they duplicate the virtual table to a fixed mapped address and change the VPTR to point the new duplicated virtual table. Another technology is called GVT. Well, they replace the VPTR with a hash number, and together with the hash number of the desired virtual function, they can look up in a global virtual table and call the desired function. Well, both of these techniques will introduce overhead to runtime performance. So we thought we could introduce a new technique for sharing polymorphic objects between processes efficiently. And we implement these techniques with LLVM and compare it with previous techniques. Performance evaluation using macro benchmarks shows that our technique will introduce less overhead, and we also apply our technique to several application scenarios. Okay, let's introduce our technique called indexed virtual tables. The basic idea is to replace virtual table pointers with indexes. Well, it's basically inspired with the work of Bacon, who has just gave us the talk this morning upstairs. These indexes are used to look up in a virtual table pointer array. Well, it can be located anywhere, and this array will contain the actual VPTR. Well, since the VPTR is generated by compilers, our modification has to be in the compilers too. So here is the new compilation flowchart. At first, developers can give us hints on which classes are involved in sharing. Well, they can write a specification about it. This specification will be used in two ways. The first way, we translate the specification into a C++ code that includes the VTPA. Here is a simple example. We have four classes. For class A and class B virtual inherit class A and class C2, and class D inherit class B and class C. In this situation, we can see that the objects of these classes will look like this in memory. So the generated VTPA will look like this. It will contain all 8 VPTRs. Well, as a result, we actually map each VPTR into an index. Well, the second way of using the specification that we give hints to the compiler transformation. The compiler transformation we took place in two places. The first one is object constructor. Well, there's an ordinary object constructor here, and the corresponding LLVM IR code will look like this. Well, there's a sub-function that is responsible to fill the VPTR into the object. So our job is to locate this long gray IR expression. This is the actual VPTR, and replace it with its corresponding index. As we can see, this operation doesn't introduce overhead at all. It shouldn't, if it doesn't improve the performance. Well, as a control, the previous DVT technique, this is the pseudocode, and before the actual construction routine, they have to binary search, doing lookup tables, something like that. So they will introduce overhead to the object construction procedure. The second part of compiler transformation happens when dynamic dispatch. Here is the virtual function is called, and the corresponding LLVM IR code will look like this. Basically, they look for the virtual table through the VPTR and look for the virtual function pointer and then call it. Well, since we replace VPTR with index, so we add our procedures to it. We add 2 load instruction and 1 add instruction. As we can see, we introduce some overhead, but it should be neglectable. It's really simple. As a contrast, the previous GVT technique, they transform every virtual function to a non-virtual function and a friend function. In the non-virtual function, they search for the friend function with the hash code of the class and the hash code of the function. Combine them together and search in a hash table or something. Then call the friend function. So as we can see, the GVT technique will introduce overhead to dynamic dispatch. Okay, at last, when the developers cannot provide a specification, we can help to generate one. Our current implementation is simple. We just find and record all virtual table pointers and make it a table. This solution, we will refer this solution as IVT Auto. As we can imagine that IVT Auto will introduce more overhead than the original IVT, but the following evaluation will show that it's not that bad. Okay, let's see the evaluation result. First, we generate multiple macro benchmarks. For each macro benchmark, we define C classes, and each class has F virtual functions. Then we create R shared memory regions and construct N objects in total for each class and in each region. And at last, we call each virtual function of each object once. Okay, this is the methodology. Here is the result. As we can see that DVT technique, the blue line, will introduce overhead to object construction procedure. And the GVT techniques, the green line, will introduce overhead to the dynamic dispatch procedure, while our proposed IVT technique will introduce non-negligible overhead. Okay, we also apply our techniques to several application scenarios. The first one is XML transformation. In these scenarios, some XSLT files serve as style templates, and XML files are style-independent web pages. If we want to translate the XML file into different styles of web page, we could share this parsed XML object and reuse them. As a result, that the XML parsing procedure will is omitted in the following using our technique. Well, if we focus on the first part, the transformation to HTML, we'll see better that our IVT technique introduce less overhead than previous technique. The second application is facial recognition. It's similar that XML files will store facial features, and we can take images from different cameras, and we want to detect faces from these camera images. Well, unfortunately, OpenCV library, which is always popular in image processing, their data structure to represent a facial feature, which is casucate classifier. It contains virtual function, okay, which makes the object and polymorphic object. Well, if we want to share this parsed XML files or the parsed facial features, well, we can omit the load facial feature file. This procedure, we can save a lot of time on that. Also, if we focus on the facial detection, the main facial detection routine, we can see that our IVT techniques also introduce less overhead than the previous techniques. Okay, the third application scenarios is robotic middleware. In these situations, all kinds of messages are generated and sent constantly. We have to we have to carefully handle their lifetime and the concurrency and that. So we carefully design some data structure inside a shared memory. Then we thought, why don't we design a base class for them? Unfortunately, if we want to design a base class, we have its destructor has to be virtual, right? So these becomes polymorphic objects in shared memory. And in this case, we compare our results with some popular frameworks. The ROS framework, which is robotic operating system, is commonly used by the robotic community. It's based on socket, so its performance is like this. And the researchers from the Institute of Technology of Zurich, they improved the basic framework of ROS, and they used shared memory to improve the communication latency. But as we can see that the performance improvement is not very noticeable because they use serialization. They serialize each message into the shared memory and deserialize to the receiving process. Well, by using our IVT technique, we can directly share the messages inside the shared memory. No movement, no copy, no serialization at all. So the communication latency is constant. Okay, that is basically all I want to introduce, and let me conclude my work. We have presented IVT, an efficient technique that enables directly sharing of polymorphic objects across processes, and evaluation results show that our technique brings minimal runtime overhead, and we have also applied our IVT technique to 3 application scenarios. Well, our implementations can be found at GitHub. Okay, that's all. Thanks, and you are welcome to visit my lovely campus. Thank you.
Okay, questions? Yep.
So how do you deal with the pointers? Because some objects should contain pointers.
Yes.
Don't you have to do some pointer switching or sort of serialization?
Yes, as I have mentioned at first, we have to manually change pointers to the relative offset.
So, I'm interested in that overhead. That's part of the overhead.
Well, that's an interesting question. We didn't measure that, but well, as I can imagine that this, well, let me take back. Okay. Oh, no. Yes, there's a class implemented in Boost library, and it's relatively very simple. So I don't imagine there's much performance overhead by this class.
Other questions? So it wasn't entirely clear to me what the impact is. So it's clearly better than this GVT approach, and it's also slightly better than the DVT approach. But in absolute terms, in terms of affecting an actual application, so we saw this robot case study, but they didn't use either DVT or GVT, right? So they
Right.
used a completely different approach.
Right.
So with respect to GVT or DVT.
In the third application, in the robotic middleware, we didn't show the comparison, but the result of DVT and GVT is also good because there's other computation overhead latency, and that will we don't show that significant result. So basically they are the same. Well, if you are interested, their solutions is also good. Well, in fact, we before we do our work, we talk to the authors of the UIUC work, and they are not prepared to open source their works. So we thought, well, why not? We can do it ourselves.
So infinite improvement. That's very good. Okay. Any other questions? Right. Let's thank the speaker again.
Thank you.